So hello everyone. Yeah. Okay, Brent. I'll probably have to turn off the sound because I can hear myself. Oh, so if anything, just type it into the chat. Okay, so everyone, hello from the quarantine. I was supposed to be there with you in Liptovská Teplička, but unfortunately I tested positive, so I had to separate myself from the rest of the society. And the talk I will give you today is about a topic that is separated from the rest of the physical society as well. It is something like in a far, far away distance away from ordinary physics we are used to. And it's about the physics that happens on the Planck scale. And I will have 3 talks about this topic that I'll split into 3 different subtopics. The first is the Holy Grail of physics, which will be today lectures about our efforts to find a single unifying theory that would describe all physics that we know. Tomorrow I'll have 2 lectures. And the first one will be about matrix theories, and it will be more maybe technical presentation. And again tomorrow, but afternoon I will talk something about black holes and the secrets they have. Today's topic will be more or less conceptual, so we won't go into many details. The matrix talk will be not mostly technical, but more technical than the first and the third one. And the third one will try to be a little bit, maybe even like about phenomenology. So maybe some possible observations that we can do about Planck scale physics. So if you have any questions, don't be afraid to ask, but I won't hear you, so you'll have to type it into the chat or ask Dominic to do it for you, so I get at least some kind of a feedback. Okay, so today's lecture will be about the Holy Grail of physics. And the basic idea is this tree. If you can see the arrow, it's going from top to bottom, and it marks the evolution in time. So basically up in the picture is a prehistoric time, and down there is hopefully our future. And the physics so far looks, okay, you don't see the slides. Okay. So let me try again. Maybe it was just a problem with having them full screen. Okay, can you see them now? Dominic, can you see a tree? No. Okay. I'll try it here. Share screen. Share. What about now? Now I can see a reply. Can you just unmute yourself and say if you can hear me or if you can see it?
Hey, we can see it.
You can see it, Grant. Okay, so this is how I view physics. So it's like a tree, and a couple of thousand years ago or hundreds of years ago, we're up there. What do I mean by that? I mean that when we were trying to describe what we saw around us, we used many different theories. We had a different explanation for volcanoes, a different explanation for how fire works, how lighting works, etc. And gradually what happened is that we realized that many things can be explained by just one. So for example, Newton discovered that the laws that govern the movement of celestial bodies is the same law that describes how those apples fall from trees. So we observe some kind of unifications. And it was firstly a lot of prehistoric stuff, but then when probably physics started or began is during Newton's revolution, when he realized that, well, basically the celestial physics and the earthly physics is the same thing. And he found some law for it. So it was basically moving from those many leaves to the first parts of the trunk. So many different events or phenomena suddenly got the same explanation because of gravity. And people started liking this, so they were trying to figure out, well, aren't there some universal laws that govern, again, way too many things, for example, like electricity? So the first big revolution was done by Newton, who realized that, well, those two are the same thing. The second was probably done by Maxwell. Both electricity and magnetism were known before Maxwell, but were understood as two different theories. People knew that when they, I don't know, played with amber, that it will attract dust particles or something like that. And they also knew there are some minerals mined somewhere in Greece, in a city called Menisa. And those minerals make iron act funny. It can move the iron without touching. So those were two different theories, electrism and magnetism. And what, well, many people start working on, but Maxwell finished, is that he unified those two things into a single theory of electromagnetism. That was a huge leap forward. Also because this was probably the first time ever in human history when mathematics were used to derive or to find new physics. When Maxwell put his equations together, they didn't fit perfectly. There was like a piece missing in there. They were mathematically inconsistent. So he just put this new term into equations, and he described that this is what we now call Maxwell's displacement current. So he used mathematics to derive new physics, and then point his finger for an experimentalist to find this new phenomena, and these were confirmed. So basically, Maxwell started theoretical physics, the idea of figuring out how does the universe work by using mathematics. And as you all probably know, well, this wasn't the end of his job. He also found that, well, by joining electricity and magnetism together, he forms the equation that also describe light. So actually optics joined this new theory. So again, like those things were coming together, many different theories described by a single one. So this was probably the stage somewhere around here. So this was basically the main theme of the previous century, basically joining theories together, trying to unify them under a single model, for example, or single formalism at least. So for example, people realized that, well, electromagnetism can be described as a gauge theory, but not only electromagnetism, we can also describe electroweak forces. So the weak nuclear force joined the bunch and basically form something called electroweak theory, and then also the strong force joined as well, this newlywed bunch. So from this particle side of the theory, everything worked perfectly. Basically, everything we see around us, apart from gravity, can be described on the fundamental level by what we call the standard model of physics. Now, there are two types of unifications. And what I mean by unification is the thing we call the standard model. Basically, the idea that, well, the forces can be described as a part of a single model. I don't mean necessarily it has to be the grand unification, meaning that all the forces has to be like a part of a single force that undertook some symmetry breaking and split into different forces. Just having a single theory that describes everything, and the single theory can contain many different forces, that would be fine with me. So this is what I called a unification. So it doesn't have to be like the standard sense of the word. So this first branch worked perfectly well. This was the theory of particle physics or the quantum theory. The second huge branch is basically the gravity. So first big Newton discovery is that the gravity on Earth is the same as gravity in sky or the rest of the universe. And there weren't many huge leaps, as in the case of particle physics, but basically the largest one was done by Einstein, who basically derived a single theory which envelops the Newton's theory of gravity, but also can explain some other phenomena as, I don't know, bending of light by sun and things like that. So, and this is our situation now. We have two different theories that either single-handedly or together can describe nearly everything we see around us. Now, we believe that maybe they can come together somewhere, and I'll talk about this more today. Well, why does this work? Why do we even tend to do this? So from our perspective, I think it's about, well, finding nice theories. A nice theory is a theory that can explain as many things using as few assumptions as possible. So for example, if you can derive everything about electricity and everything about magnetism using a single theory instead of two, that's a step forward from our point of view. So we tend to do this, and we appreciate if we succeed in doing so. But also, it's like when we find something that we cannot describe, the first thing we try to do is use all the theories we know to describe the new phenomenon. So this is basically the natural explanation for why everything fits in a picture that we are used to have. Because when we find something new, we try to explain it within the theories we already know. So it's a very natural way of moving science forward. Now, the tricky question is, why does it work from the perspective of nature? Why should nature prefer having a single theory that explains everything instead of having 17 or 2071? And probably this is a philosophical question, I don't know, but it's an interesting question to ask. So I understand why we try to do this, why we try to explain everything we see around us using a single theory, but I'm not sure why nature allowed us to do so so far. Maybe there's a good explanation for it, I don't know. Okay, so what happens down there in the bushes? It's those bushes down here. So you know that this should be the place where quantum meets gravity. There's very little we know about this, but we have some estimates on what scales should this happen. And basically the idea is looking at the fundamental constants of nature. We know there is a small number of them. We have a lot of physical constants. You can buy a book full of different physical constants, and most of them are not fundamental. For example, you can find a physical constant, which is, I don't know, the density of water at 0 degrees or 10 degrees Celsius. And this is a physical constant. Every time you try to measure this, you will get the same number. And we believe anywhere in the universe, you will do this measurement, you will get the same number. But it's obvious that the density of water at a given temperature isn't a fundamental parameter of the universe. It's something that can be derived from something deeply hidden. So for example, from the size of the electric charge of a single electron and Planck's constant and etc. And the list of parameters we believe are fundamental is very short. And it has the Planck's constant, the Newton's gravity constant, the speed of light, and some more. There is an extended list of parameters, for example, like coupling constants from the standard model, but at least some of which we believe can be derived from a theory we don't know at the moment. So maybe the list of real fundamental physical parameters is very, very short. Maybe some believe it only has one single parameter from which everything else can be derived. We won't go that far today. Maybe we will, but at the moment, we'll talk about the current state of the art. Current state of the art is, well, we have those three: Planck constant, speed of light, and gravitational constant, and they have weird units. And what you can do with them is that you can try to mix them together in a way to produce something which has dimensions of length, mass, time, temperature, etc. It's a simple exercise that you can do for yourself, that there is a unique way how to do it. So if you take the Planck's constant, the gravitational constant, and the speed of light, there is a unique way how to derive a new unit with a dimension of length, for example. So you cannot do anything else than just this. Now, the value of fundamental constants is very important. For example, why is gravity weak? Well, gravity is weak because Einstein's or Newton's gravitational constant is very, very small. Had it been 10 to the 20 times larger, then probably Earth would collapse into a black hole. Now, the current state is, well, Earth with its entire mass is pulling you down, but it isn't that difficult to stand up or even jump or do something like this. So you can just basically move the other way as the 10 to the 50 particles is trying to force you to move. Again, another constant is the speed of light. So we know that the velocities in our universe go from 0 to speed of light, which can be set to 1 in convenient units. And it tells you that whether you are allowed to use classical physics or you are forced to use relativistic physics, kinematics, dynamics, whatever. So it's setting some kind of scale in our universe. Most of our lives, we live or we move with respect to each other at velocities that are basically 0 with respect to the speed of light. Had we been moving at speeds comparable with the speed of light, we'd see all those funky stuff like time dilation and length contractions and so on. The third constant is the Planck's constant, which is basically telling you that at what scales are quantum effects important. At what scale do you have to consider that the particle can move through both of the splits at the same time? So the three fundamental constants gave us some important scales in our universe. And now we believe that if we mix them together, then again, they are pointing towards something important, some important scales when something is working differently to what we are used to. And basically, it's easy to interpret them, at least in those three scenarios. So we believe that Planck's length is the smallest possible length that we can distinguish in our universe. Basically saying that if 2 points are separated by a single Planck length, you cannot distinguish them. They look the same to you, and not only to you, to the universe. The reason why is this so is, well, imagine you would try to distinguish 2 particles that are separated by Planck's length. To distinguish them, you would need a photon with a wavelength that is on the order of Planck's length, 10 to the minus 35 meters. Now, if we compute what would be the energy of such a photon, remember that the energy is 1 over wavelength. So the energy would have to be huge. Actually, it would be so huge that the photon would be hidden under its own event horizon, and it would form a black hole. So if you would like to distinguish two points separated by a Planck's length, you cannot do so, because doing so would create a black hole and would prevent obtaining any information. There are many other ways how to explain this. For example, if you have a particle and would try to squeeze it into a Planck's volume, then the energy density would be large enough to form a black hole. So this is the interpretation of the first Planck unit, Planck's length. Planck's time isn't so clear. Some people tend to interpret this as like the shortest time step available in the universe. So maybe even time is discrete, and basically this is like the frame per second of our universe. So length of one time frame is 10 to the minus 44 seconds. For other people, for other physicists, this is basically the starting time of the universe. So it's like at this time, basically the laws of the nature as we know them appeared, and before that it was different physics. Now Planck mass is weird because Planck's length, Planck time are very, very small. Planck's mass is like, it's lighter than me, but it's way more massive than proton. So it's somewhere in between. So it seems to be a weird Planck unit, but the interpretation I tend to follow is that basically this is the largest mass of a single particle or a point particle. So basically this will be like the upper limit of the particle physics. And we will see during the third talk that this is also actually the mass, the smallest possible mass of a black hole in our universe. Okay, so the situation so far, we know quantum theories or theories of particle physics, we know the theory of gravity, and we try to figure out what happens down there in the bushes. And taxpayer can ask you, why do you even care? Like, is there a reason, or is it just because you want to feel better about yourself and joining everything into a single theory? So is there even a motivation for joining together quantum theory with gravitational theory? And there are two reasons. The first thing is that, well, quantum theories are important when things are small. Gravitational theories are important when things are massive. And we know that inside a black hole is something what we call the singularity, and the singularity is both very small and very massive. So we believe that that singularity can be understood only using the theory of quantum gravity. And the other important point is the beginning of the universe. Well, the word point was probably a Freudian slip, but basically at the beginning of the universe was very, very dense, and it probably wasn't small, but it was so compact that even on a quantum scale, gravity was important. So it was so dense that it could have been described only by the theory of quantum gravity. So if we want to try to understand how did the universe begin, what happened during the first couple of Planck times, we probably need to know the full version of quantum gravity. Now, people tried this before, like joining gravity with other forces. And I'll tell you about an idea that probably proved out to be wrong. It seems to be wrong or incorrect, but there are some important ideas that, well, physicists were persuading for next decades and are still using. And it's called Kaluza-Klein theory. And the basic idea is this. So Kaluza looked at the main ingredient of the Einstein theory of gravity, which is the metric tensor, this G, which tells you how to measure distances in a curved space-time. And if you know this metric tensor G, you know everything about the curved space-time, you can derive all the forces of gravity or anything you would like to know about the space or space-time. So this basically contains all necessary information you need to describe gravity, those 16 Gs. Then we know that Maxwell equations can be expressed in terms of vector potentials. There are 4 of them, jointly called A1 to A4. So first of them is the scalar potential, which we used to call small phi, and then the 3-dimensional vector potential, which we used to call A. So what Kaluza realized that, well, the first thing is a 4 times 4 tensor, the metric tensor of gravity. The second one is 4 times 1 vector. So maybe I can just, well, join them together within a single 5 times 5 tensor. Now there was a single empty space which he filled with a field that is called dilaton. And what he did is that he imagined that, okay, imagine that this is a metric tensor from a 5-dimensional space-time. Usually, the Einstein gravity works in 4-dimensional space-time, 1 time plus 3 dimension. So he enlarged the tensor by 1 column and 1 row and said that, well, maybe this describes something in 5-dimensional space-time. Let me write down the same Einstein field equations as are used in 4 dimensions, but using those 5-dimensional objects. Those are with tilde here. And what he found out, to his surprise, is that those describe not only gravity, as he knew. So this is the first part, but also this gravity is coupled to electromagnetic fields. This is something called Kaluza miracle, that basically he recovered the gravity coupled to electromagnetism from considering 5-dimensional theory. Also, there are the dynamics of this new, not dynamics, the interaction with the new dilaton field. But he didn't bother about it that much. But the question was, well, obviously we live in 3 spatial dimensions plus time. What can I do about the 4th dimension? Or the 5th dimension in a space-time point of view? So he basically assumed something called a cylindrical condition, which says that none of the dynamical fields of the theory depend on the new extra dimension. So he used 5-dimensional theory to derive the 4-dimensional laws, and he prevented us from knowing anything about the extra dimension by just saying that, well, this dimension is forbidden, you cannot go there, but it affects the equations. Then Klein came and asked himself how this equation looked on a quantum level. And he realized that if we say that the 5th dimension isn't forbidden, it is just very small. It's curled in a circle. Plus, we know quantum physics. So we know energies can only take discrete values. And for a field to go around this fifth dimension, the circular one, in a non-trivial sense, it would require to have very small wavelengths. That means very high energies. So if this new extra dimension is small enough, that we cannot access it without using very, very large energies. Basically, the energy you need to use is so large that the wavelength is on the order of the circumference of the extra dimension. So this alone would be very interesting. And there was something extra. The first thing is that, well, not only that, Kaluza described gravity and electromagnetism within a single formalism. He was even able to derive or to set the size of the electric charge by the size of this extra dimension. So if this extra circle is very large, then the electric charge that appears here is very small and the other way around. So it means something very, very profound. It means that the physics that we see in those extra 3 spatial dimensions plus times are affected by the size of the invisible dimensions that are too small to be tested or visited directly, but still their presence is felt by the large spatial dimensions. The second interesting thing is that, well, so Kaluza and Klein realized that you can describe basically electromagnetism in Einstein theory by adding a circle to every point of space. This is like attaching a S1 circle everywhere in space. And this is basically how electromagnetism works, right? We know that it's described by U1 gauge theory. And U1 is basically the symmetry of a circle. So we can understand electromagnetism as, well, basically gauge theory with S1 symmetry. But usually we think about those gauge symmetries as symmetries of an internal space, not a real space. And in Kaluza-Klein's theory, this was a real spatial dimension that was just inaccessible to us. So another interesting point of view. Okay, so the current state of art or the current understanding of this theory is that, well, basically it cannot be tested because we can compute what should be the energies to see those extra dimensions, and we cannot do so at the moment. Actually, people at the Large Hadron Collider considered finding evidence of extra spatial dimensions. Maybe it was 14, 15 years ago with no success. And I won't go into details, and I'm not sure if anyone even believed that this is possible, but well, people try to do so. So it still isn't like completely excluded by experiments, but it's not like a mainstream area of physical research. But it was a nice idea, and it probably had something to it. Okay, so what we are trying to do since Einstein is trying to merge quantum physics with gravitational physics. So basically we are trying to formulate a quantum theory of gravity. Now we can do it these 2 ways, because we very well know how to do quantum physics and very well know how to do gravity. So one idea is, well, basically take a gravitational theory, for example, the Einstein theory of gravity, and just try to quantize this theory. And this is very tricky and actually seems to be impossible. So for example, you can take formulation of gravity using Hilbert-Einstein action. So you define the action for the curvature of space-time. And from this, you know that you can describe ordinary gravity. Now, you can formulate quantum mechanics in terms of path integral, meaning you have to to get a mean value of an observable, we have to integrate over all possibilities, over all possible paths, and assign a complex factor to each of the paths. Now, this complex factor is described by the action, so you can take the gravitational action. And basically, what you need to do is integrate over all possible spacetimes and get the results. And this is nearly impossible to define precisely. You can say like, okay, integrate over all possible spacetimes, but what does it even mean? Do we have to integrate over all possible, I don't know, like global geometries or different local geometries or different number of like topologies, like universe with a hole or something like that? So it's very unclear how to do this properly from this side, how to basically consider all possible space-time geometries. So this way didn't prove very useful. You can try it the other way around. We know that gravity contains waves. These are the gravitational waves that have been detected recently. Now we know what is the spin of those waves. They are of spin 2. So you can take a spin 2 particle and try to plug it into particle physics. And again, this doesn't work. This produces unresolvable infinities. So just plugging relativistic particles or particles of gravity and plugging them into field theories, quantum field theories, doesn't work either. Now, there are some people that believe that actually this isn't a complete disaster and this approach would work with some small fixes, and this is called asymptotically safe gravity. So that actually on the largest scale, something happens to the, on large energy scale, something happens to the gravity, it behaves differently, and actually those two theories can be merged together. So, well, maybe we will find a simple answer like this, but otherwise I probably have to conclude that neither of those approaches, plugging quantum into gravity or plugging gravity into quantum, so neither of those seems to be working at the moment. Now, there are many candidates for a new theory that could fulfill this long-sought goal of basically merging quantum with gravity. And a theory that actually achieved this absolutely by accident is the string theory. String theory was derived as a theory to explain some behavior of particles that was observed in particle accelerators, something called the Regge curve. So people start working on this theory, and the basic idea is that, well, okay, so usually we have point particles. Point particles are moving in a space-time and they produce something called word line. So basically the time now goes up. Those are spatial dimensions. So if you fix the time, the point is only a point, but this is a point flowing through time. Now, what is a string? Basically the same thing plus one dimension. So at a fixed time here, it's a one-dimensional object. And this one-dimensional object is flowing through space. Now, on a single particle word line, you can define something which is called, and I forgot the word now, like the time of the for that holds for this point, like a personal time. Here you have two-dimensional surface in the space-time. So there are two dimensions, the temporal one and spatial one, called sigma. Now there are two different cases you need to consider, basically something called an open string, which is this case, a string with two open sides, or a closed string that basically forms a loop, and the loop is flowing through time. Now, again, it's a simple exercise that you can derive the laws for a relativistic particle by considering the action for this word line. So the idea for the strings was the same. Basically, in the same manner, define the action for this so-called world sheet and use it to describe the equation of motion. So basically, it's like you integrate over this surface in space-time defined by the flow of the string in time and integrate this thing, this square root, where x basically is the coordinate of the string in the space-time, and it depends on two parameters, tau and sigma. So this is rather straightforward. There are some symmetries that you can utilize. And in a classical theory, it's nothing super interesting. The funny thing happens is when you try to quantize this theory. So basically take this action and you quantize it in a very similar way to what you are used to in ordinary quantum mechanics. Basically setting some commutator laws and define some kind of algebra. And in some sense, it's slightly similar to analyzing quantum oscillator. For quantum oscillator, you define the Hamiltonian, the creation annihilation operators. In a string case, it's slightly more complicated because the algebra you derived, it's called Virasoro algebra, and it's slightly more complicated, but you can still work along the same line. So you can use it to derive the energy spectrum, for example. In the quantum oscillator case, we know that the energy spectrum is basically the energy is a constant plus something, plus some integers. Now, in the case of strings, the spectrum is basically defined by this. N is an integer, and m squared is like the mass of the, or the energy of the string. So you can basically derive the spectrum, and there are some interesting properties because, for example, you can derive a theory of interacting strings by considering diagrams that looks like this. So basically, this is a single string coming from left, second string coming from right, then they merge together and split again. Now they merge with the whole, etc. So you can actually derive a theory of interacting strings in a rather simple way. Well, okay, not so simple, but in a way. Now there are some issues. Now the quantum theory is consistent only in 26 dimensions. There are some quantum anomalies that cancel only if there are 26 spatial dimensions. You have closed open strings, not an issue. And the surprising fact is there is gravity in a certain sense, in a sense that if you look at the spectrum of quantum strings, it contains massless particles of spin 2, which basically is the graviton. And this was something that couldn't be achieved in a classical way, like taking graviton and plugging it into quantum field theory doesn't work. But here we have a quantum theory with graviton that unfortunately works only in 26 dimensions and has no fermions inside. So far, this is just a bosonic theory. And also it contains tachyons, which is basically particles that move with velocities about the speed of light. If you plug n equals 1 here, then you see that basically the mass squared is negative. So you have basically something that looks like an imaginary mass. So there seems to be some issues with this theory. It's nice. It's a quantum theory that contains both bosonic particles and gravitational particles, gravitons, but had some issues. So this was the bosonic string theory. People realize what you can do is you can define a superstring theory. Basically, you take the action and you just make it supersymmetric. Again, do the whole procedure, derive the algebra for quantization, quantize it, and we will find out that suddenly this works in 10 dimensions only, 10 space-time dimensions, which is like, that's a lot, but if you are used to 26, then 10 seems to be the right way to go. So the superstring theory works in 10 dimensions. Now, tachyons are gone from the theory. So there are no particles with imaginary mass, which seems again that we are moving the theory in the right way. Unfortunately, the nice thing about the string theory was it was a single theory. It had basically no free parameter apart from, for example, the string length or the string tension alpha. Alpha is the string tension, ls squared, or ls is the string length. So you have a very small number of fundamental constants and everything else is fixed by mathematical consistency. So that would be like Maxwell's wet dream. Now, unfortunately, forming a superstring theory, people figure out it's not unique anymore. There are actually 5 of them, which basically boils down to the fact that you can define different boundary conditions for the fermionic degrees of freedom. So suddenly, on our road to finding a single physical theory, we found 5 different, and they are called string theory of type 1, type 2a, type 2b, and then 2 heterotic string theories, SO32, and 2 exceptional theories. I won't go into details. What does this mean? What are those funky names? I'll just tell you one thing, and the thing is that what people realize that actually those are not 2 different theories. Those theories are connected by a string of dualities. There are 2 types of dualities, S and T, in this picture. And basically, duality is that you have 2 theories that under some circumstances basically look the same. So for example, if you take those 2 theories, 2b and 2a, and you take one of those dimensions and curl it up into a small circle in one case and very large circle in the second case, they will look the same. They will have the same particle spectrum, etc. So what Edward Witten realized is, well, this is again the elephant in the room scenario, or the elephant in the dark room scenario, when you basically probably are poking the same theory just from different angles. So basically, he conjectured that those 5 theories of superstrings are connected by basically a web of dualities because they basically stem from a single theory. They are all just aspects of something more fundamental, and the more fundamental thing is called the M theory. Now, he coined the term M theory without telling us what M stands for. So people are now, well, basically guessing, and somebody calls it like mother theory, because it's like the mother of our theories. For someone else, this is the mystery theory, or actually matrix theory. So we don't know, but this seems to be the fundamental theory. Okay, so now we know that we live in a universe with 3 large spatial dimensions. We can go back and forth, up and down, left and right. So why does the superstring theory insist of having 6 large spatial dimensions? 6 small and 3 large, so 9 together. So the idea is that, well, maybe the extra dimensions are curled up. They are very small, in the same way as in the Kaluza-Klein theory, so we cannot see them directly, but they actually affect the physics around us. And the idea is that, well, those extra dimensions can be curled up in a way to reproduce what we know as the standard model of particle physics plus gravity as we see them in our universe. And if you curl those dimensions differently, you will get like different set of physics. The unfortunate part is it seems that just like a ballpark estimate, the number of different compactifications of those extra spatial dimensions is 10 to the 500. So it's impossible to just go over every possibility and verify whether there is the standard model of particles plus gravity or not. So we need to find some clever way how to do this. And this is a mainstream area of physical research, like trying to find our physics within the landscape of all possible physics described by the M theory. Unfortunately, the fundamental equations for the M theory are not known. And tomorrow I'll tell you about one possible case that somebody basically guessed that maybe it will look like this, and now we are verifying whether this works or not. If this equation can actually contain all physics that we know or not. So we don't know, we knew the exact formulation of the string theories, but we don't know the exact formulation of the M theory, but there are some conjectures. And now, basically the current situation is like this. Some people believe that the M theory is correct, but it's, I don't want to say close to impossible, but it's extremely difficult to derive our physics from it. So basically they are just, okay, they just said, okay, this is not for me, I'll do something different. So some people like moved away from this area of research because it's like seems to have hit the wall. Unless we find a new way how to navigate through the landscape, it seems that we have been stuck. Maybe we found the correct theory, but we cannot prove it using the means that we know of. Then there is another approach that maybe actually this theory isn't correct. Our universe doesn't work like this. But there are some important take-home messages. The first one is that quantum theory of gravity can be formed. It's not mathematically impossible. Like this is a counterexample. If somebody tells you that gravity cannot be quantized, it can be quantized. But maybe we don't know how to do it for our universe, but we can do it for someone who can call it like mathematical models. Now, and the third thing to take home from the M theory is basically something called gauge gravity duality, which seems to be another mainstream area of research. And it isn't clear whether this holds for our universe or not. But some people believe that this is actually a very fundamental property of physics that we didn't notice in our universe, because in our universe gravity is very weak. But in those mathematical models of M theory, what people, I mean Juan Maldacena, noticed is that there seems to be a duality between gauge theories and gravitational theories. Gauge theory is a quantum theory of interacting particles. Gravity is gravity. And what he noticed is basically those seems to be like two sides of the same coin. So there is actually, you have a theory that on one side can be described as a gauge theory and on the other side as a gravitational theory. And the M theory provided a very simple and testable example of this gauge gravity duality. And a lot of research stemmed from this idea that, well, okay, maybe we can try to derive new laws of nature by assuming that there is a duality between those two theories, or those two approaches actually. Okay, so in the last 5 minutes, I'll just tell you something about other approaches to quantum theories of gravity. Because the string theory or the M theory isn't the only one, it just proved to be, I have the tendency to say most successful, but it's hard to measure success with untestable theories. So let's call it the most popular is the M theory. And the second most popular is something called quantum of gravity, which basically formulates formulates the gravity as a gauge theory first, and then quantize it. And it's quantized in terms of small loops in a manner similar to something called spin networks or spin glasses. So it's a different approach that seems to be successful in some cases, but not so much in others, but it's a huge other mainstream area of research. Now, there are some smaller areas. The first one is called causal set theory, which is basically the idea that, okay, remove everything from physics that we know and try to build it from the simplest possible blocks. So in this case, you have basically a set of points that are organized in some way, and you try to define some interaction between those fundamental building blocks that would reproduce the physics that we know. So for example, to reproduce Einstein field equation or something like that. So this approach is rather popular, maybe because it's technically not so difficult and people are playing with this idea a lot. So how would the universe work if you just build it from simple building blocks governed by some simple interaction? And this is something similar to something called causal dynamical triangulation, which is, again, very similar idea. Is basically have points of space that you can connect together to form small triangles. And this can describe, this is known to be able to describe different spaces with different curvatures. Because if you remove some of those triangles, there is some hole that has to be fixed by gluing things together. So again, this approach isn't technologically so difficult or mathematically so demanding, and it had some successes, but it's working mostly in small dimensional cases. So it's very well explored in case of two-dimensional spaces. And the third approach is something completely different. This was coined by Wheeler. It's called it from bit. And during last decades, this became it from qubit. And basically the idea is, well, maybe we shouldn't try to merge quantum physics and gravity. Maybe quantum mechanics or quantum physics is the fundamental law of nature, and we can derive gravity from quantum theories. And this again had some successes, not overwhelming, but it's moving forward. So there are many approaches. It's not only about the string theory, but string theory found or reached at least many partial successes. And at the moment, it's a very successful theory, at least from a mathematical point of view, in the sense that, well, it's a very complicated theory that is consistent and that seems to be containing everything we see around us. It has gravity, it has all the particles we need. The problem with the string theory is that it does have a lot of stuff that we don't want to see there, like more particles that we know of, more dimensions. And there is a good chance that actually there is an explanation why those things aren't actually present in the theory or why they disappear, but we need to figure out how. So for example, by curling the extra dimensions, they will also make most of those particles very massive, so basically unobservable in our universe, and maybe we can even find a standard model plus gravity in there. So thank you for your attention. This is the end of the first lecture. And if you have any questions, please ask Dominic to type them in the chat.
We have already all this, but you didn't hear, so we are happy to applause once again.
A little bit.
Okay. So, are there any questions or comments?
Yes.
I see no questions, so let me ask if you can comment more on this. Like people always ask, from the popular point of view, why there should be exactly 10 dimensions or 26 for the bosonic string. You said that it's rather technical and you preferred not to go into details. But if if a younger sister asks somebody here, so why is it so? Is there a better answer?
There isn't a simple one.
It's not.
I can write a comment.
Yeah, you write.
Yep.
Can you please flash the Planck Binks slide with the time mass?
Have you heard? You write.
I heard that it's about mixing space and time.
Can you flash the slide with
Okay.
mass, the length and time?
This one?
With Planck mass.
Okay. Sorry.
Because this one, I have noticed that the Planck constant enters these quantities in very different fashion than the other two. That always when you send Planck constant to zero, you get zeros, while when you send, for example, G to zero, what's that? Planck mass diverges. That clearly quantum mechanics is different in something than gravity and special relativity.
Well, but does this tell you the exact number, like why 10 and not?
It doesn't show exact numbers. It just shows that the fundamental constants do not work in the same. All the fundamental constants do not work in the same fashion.
Yes.
But to be honest, I have seen this probably a million times, and I noticed it for the first time. So I'm not sure what that means. That was a comment, not a question.
Okay, so have we recorded the?
Yes.
So then I think that we will be able to go maybe over the lecture or some parts of it if it was not completely clear, and we may have more questions later.
Yeah.
So Samo, I would like to thank you very much for this first lecture. We now have to take a break, and we'll get in touch with you tomorrow morning.
And maybe just one more point, that probably the easiest answer to your question is that it's related to the symmetries of the space and the possible representation that can be formed. So, but it's still not a popular answer that you can just throw on your friends.
Yeah,
but for students, it's probably the easiest to approach.
One answer which I might be trying to throw at my friends is that there is an infinite series to be summed, and it only makes sense and gets analytical quantification with some finite answer in this number of
Yes.
Dimensions.
Yes, but it's the unfortunate that, like, from this simple calculation you get the d equals 26 by by summing all integers, and the result is -1/12. So this is another thing that isn't.
You just tell that there is an infinite series.
Yes. Yes. And hopefully they won't ask more details.
Or there should be more talk about analytical continuation.
Yes.
Any more questions or comments? So, if there are none, once again, thank you very much. We'll get connected tomorrow morning, and now we have a break by 10 o'clock.